Hello everyone, this is Xu Huanwen from Department of Electrical and Computer Engineering in University of Florida. This is a presentation for my course Pattern Recognition. My topic is face recognition using KNN and CNN. The database I'm going to use is Olivetti Faces dataset. It contains 400 images of faces from 40 different people. Each people has 10 different images. The resolution of each image is 57 times 47. Let's look at the k-nearest neighbors first. It's a common method to solve the classification problem, and it's a lazy method where the function is only approximated locally and all computation is deferred until the classification. It using the voting method to help classification, which means the result is based on the voting result in the k-nearest neighbors. We also need to choose the type of distance used in this project. The distance in this project is Euclidean distance. And we also need to select the key value, which will affect the result a lot. Before we apply KNN, we have to pre-process the data, because each image is of the size 57 times 47, which is 2679 dimensionalities. It is too big for computing distance. It needs to be decreased, but how? The way I use is the principal component analysis. It will reduce the dimensionality of input images and keep information invariance in the order of importance. It helps to decrease the computing cost and it is easy to implement. Firstly, we have to turn the samples into vectors, and then we have to apply normalizations on these vectors. These are 4 steps to apply PCA. Step 1, we need to subtract the mean response for each dimensions of X. And nextly, we have to compute the scatter matrix. And then we apply eigendecomposition on the scatter matrix, get the eigenvectors and the eigenvalue. The principal components are taken as eigenvector. Then we keep owning the top key eigenvalues and eigenvectors. The reduced representation is given by the formula. In this case, the dimensionality of our image is decreased to k. This will help us understand how PCA works in 2D samples. First step, we put the original data into the principal component space. Then we project the data onto the direction represented by the first principal component to reduce the dimensionality. The blue point is the original data, and the red point is the projected data. The green line is the error introduced by PCA. We also have to choose how many principal components we are going to use in the KNN. Here's the result of the test. As we can see, before we using 15 principal components, the performance increases dramatically, and after that, the performance tends to be stable. And when we using 30 principal components, the performance is the best. It will give us 97.5% accuracy in recognition. These figures will explain the reason. As we can see, the first 30 principal components contains more than 80% of information in the image, which is enough for us to classify the image. We have to carefully select the key value since it will affect the result a lot. As we can see in the figure, when we're using k larger than 5, we will get the accuracy lower than 90%. The advantage of PCA plus KN is that they are easy to implement, and although they are almost the simplest method in machine learning, they still beats the performance of non-machine learning method. But the problem of KN is that the performance is highly dependent on the training set. We have to choose sample from each class evenly to ensure the accuracy, and to compute distance between every 2 samples will cost much. The convolutional neural network is another hot topic in machine learning. A CNN contains different layers, including convolutional layer, polling layer, dropout layer, and fully connected layer. In convolutional layer, convolution is computing the dot product between entry of filter and input images. Let's look at the picture. See, the convolutional layer compute the dot product of the source pixel and the convolution kernel and give us the first output of this layer, which is -8. A convolutional layer has another two parameters. The depth decides how many filters are there in the convolutional layer, and the stride decides how far the window will move after each step. One of the most commonly used pooling layer is the max pooling layer. Here is an example of a max pooling layer with 2 times 2 filters and stride 2. So the 6 is the biggest in the 2 times 2 window, and 8 is the biggest in the next window, and then 3 and then 4. Max pooling layer is a way to downsample the image and decrease the dimensionalities. A common problem in deep learning is overfitting. It will happen when the model tends to remember the exact image instead of learning the features. When overfitting happens, the performance will be perfect in the training set, but if we feed in the unknown image, it will give us a poor performance. To prevent this, we introduce the dropout layer. It helps drop out node according to a dropping rate. We don't update the weights in dropout node. Only the capped node got updated after a batch of data fed in. After several convolutional and max pooling layers, the high-level reasoning in the neural networks is done via fully connected layers. Neurons in a fully connected layer have full connections to all activations in the previous layer, as seen in regular neural networks. Their activations can hence be computed with a matrix multiplication followed by a bias offset. This layer helps to finally classify input images. Here's the result of my CNN. As we can see from the figure, the learning curve converges quickly in 5 epochs, and the accuracy reaches at 100% after about 15 epochs. The advantage of CNN is the high accuracy in prediction, and once trained, the CNN can be applied on images never seen before. And the CNN has fewer parameters than multi-layer neural networks. But the problem of CNN is that it needs huge number of training data to train the network, and it will take a long time to train it. I'm going to show you how my code works. This part of my code is going to import the package I'm going to use in this code. This defines how many classes are there in the dataset. This is the size of the image in the dataset. This function is used to load the data from the dataset and separate it into the training data, valid data, and test data, and do normalizations on it. So in this slide, we load the data from the derivative phases, and then we define how many principal components we are going to use and the parameters of the PCA. Then we feed the training data for PCA. We are going to apply the eigenvectors on the training data and the test data so that we got the training and test after PCA. Here's of my code is used to print the result. So we got a confusion matrix and the mean accuracy of 97.5%. Here's my confusion matrix. As we can see, it's only misjudged one element. This is my code for CN. Same as in KN, this part is to import package, and this part is to define the number of classes, the number of epochs we need, and the batch size. This is the size of image, and this is the filter numbers in first and second convolutional layer. This line is for the max pooling layer window size, and this is a convolutional kernel size. The load data is the same as before. This function net model is to build a model of neural network. It has two convolution network, two max pooling layer, and two fully connected layers. The learning method is SGD with the learning rate 0.005, and the momentum is 0.9. This function is going to train the model and plot the learning curve and the accuracy during the epochs. The test model function is going to predict the performance on the test data. So in these lines, we're going to transform the data to the form that our neural network can be put in. So let's see the result. As I mentioned before, it will take a long time to train. 3 seconds for around average is 3 seconds for each epoch, and it usually takes about 40 epochs to be stable. In each epoch, I shows the loss function value and accuracy in training and in validation set. As we can see, the accuracy of a validation set doesn't decrease, so that means we don't have the problem of overfitting. You can see in the training set, the accuracy has arrived at 100%. The loss value is still decreasing. We're almost done. Here's the final result: learning curve, the accuracy during the epoch, and the accuracy in test sample. That's my presentation. Thank you.